Hello there. So here we're going to give the proof of the Arzela Ascoli theorem, which gives a relation between compact sets of functions and the concept known as equicontinuity. So we are going to build up to this theorem by first laying down a couple of definitions, and then we will provide some lemmas that we will prove, and then ultimately we will present the theorem in all its glory and give its own proof. So with that being said, let's get started. So the first definition that we want to present is that of equicontinuity. So the definition tells us that let f in the set of continuous functions on the real interval 0, 1 be a family of functions. Then we say that script f is equicontinuous at a point a in the closed interval 0, 1 if for every epsilon positive we can find a delta positive, so that for all x in our interval 0, 1, whenever the distance between a and x is less than delta, we have that the distance between image points f of x and f of a is less than epsilon. Now, if delta doesn't depend on the point a that we've chosen, and we can find a single delta that works at every single point a in our interval 0, 1, and for every single function f in our family, then we say that the family f is said to be uniformly equicontinuous. So that's the first definition of equicontinuity. It's important that you understand this definition before we proceed, because this is what everything is based upon. The second, now the lemma that we're going to present is has an associated name. It provides us with something called the Lebesgue number. So its statement goes as follows. So we suppose that E is a subspace of a metric space x comma t, and we suppose that calgraphic A is an open cover for E. So an open cover is a set of open sets such that together their union contains all of E. And we also need to place the added condition that E is compact. With these conditions in place, then there exists a positive real number, so that for every x in our set E, there may be an alpha in our set I. I is our indexing set, and this alpha may depend on the x that we choose, such that the ball centered around the point x in E of radius r is entirely contained in our open set A sub alpha for some particular alpha, and this alpha may obviously depend on the x that we've chosen in our set E. So that theorem has a very interesting proof. You can have a look at it in your own time. This lemma associated with the Lebesgue number helps us derive another theorem which is very, very powerful. It says that if we have a subset of functions, a family, in the set of continuous functions on the real interval 0, 1, such that it is equicontinuous at all points in our interval 0, 1, the closed interval, then this same family is also uniformly equicontinuous. So you can find a single delta that works for every single function f and for every single point a in our domain. And now we will present the proof for this. Good. Now we present the proof that we mentioned. So the theorem was that if a family of functions defined on the real interval 0, 1, which are continuous, are also equicontinuous at every single point A in our closed bounded interval 0, 1, then that family is uniformly equicontinuous. So the proof goes as follows. In fact, before I continue, let me mention that this theorem also holds if we replace our domain with any compact set. So it doesn't just have to be the closed boundary interval 0, 1, which happens to be compact. It can be any arbitrary compact set. So the proof goes as follows. Let epsilon positive be given. Then for each x in our interval 0, 1, we choose a positive real number delta sub x, so that positive, so that for all functions f in our family, we have that whenever y lies in our interval 0, 1 and y is within delta of x, that means y minus x has absolute value less than delta, then that implies that f of y minus f of x is less than epsilon upon 2. That means the image points are within epsilon upon 2 of each other. With delta sub x chosen in such a way for every single x in R interval 0, 1, we now look at the collection B of x comma delta sub x, which are the balls with centers x and radius delta sub x. For each x in our interval 0, 1. We look at this collection and we notice that it actually forms an open cover of the closed boundary interval 0, 1. It is open because open balls are open, and it is a cover because every single x in our interval 0, 1 is contained in one of these sets. Namely, it's the center of each of these sets. Now, 0, 1 is a compact interval, and this is the key point. Since it is compact, we know that there is a Lebesgue number r positive, so that for every number in our interval 0, 1, if we center a ball of radius r around that point y, then that will be entirely contained in some other in one of our open sets in our collection. So the open sets in our collection are of the form b of x comma delta sub x. So this ball centered around y of radius r is entirely contained in one of the open balls b of x comma delta sub x for some x in our interval 0, 1. And that may depend on the chosen y in 0, 1, obviously, because we may, if we take a y that's further along the interval, it may not be in the same ball as the first y that we chose, but it will certainly be in some other, its own ball will certainly be contained inside another one of our open sets. So now, for y and z in our interval 0, 1, with y minus z less than r, which is this exceptional Lebesgue number, we have that z certainly lies in the open ball of radius r centered around y. That's easy to check. And so, we know from the statement of the lemma that y and z, both being members of the open ball with center y and radius r, must be contained entirely, must be members of the open ball centered around x of radius delta sub x for some x in our interval 0, 1. And then we see that the distance between the image points of f of y and f of z, of y and z, using the triangular inequality, that's less than or equal to f of y minus f of x, where x is the ball whose centers x and radius is delta sub x. It's the ball that contains y and z. So x is a special number in this case, f of y minus f of x plus the magnitude of f of x minus f of z using the triangular inequality. And we, by the way, we chose x and delta sub x. We know that y has to be within delta sub x of x, and so does z. Z also has to be within delta sub x of x, because y and z are both contained in the ball centered around x of radius delta sub x. And because of that condition, we know that each of these values are less than epsilon upon 2. And so their sum turns out to be epsilon. And that proves that indeed, whenever 2 points in our domain are within r of each other, the Lebesgue number, then their image points are within epsilon of each other. And that gives the proof that this family is also uniformly equicontinuous. Now we present 3 theorems and 1 lemma that are going to be used as stepping stones in our proof towards the great Arzela Ascoli theorem. So we start off. Our first theorem is that if we have E, a subspace of a metric space XD, that is compact, then that is equivalent to saying that it is complete and totally bounded. So in other words, it's compact if and only if it is complete and totally bounded. The second theorem that we have is that if E is a closed subspace of a complete metric space XD, where XD is complete and E is closed, then E is also complete. The lemma that we have here is that if we have a family of functions that's a proper subset of C01 because we have this condition that it's totally bounded. If we have such a family that is a totally bounded proper subset of C01, obviously C01 itself is not totally bounded. Then this family is uniformly equicontinuous. That can be proven in a straightforward way. So F being totally bounded in C01 implies that it is uniformly equicontinuous. The theorem that we give is credited to Karl Weierstrass, which says that if our set C01, the set of continuous functions, real-valued functions from the closed-bounded interval 0, 1 to R, it itself is complete. So every Cauchy sequence in C01 converges to another continuous function, and that convergence is obviously uniform. With these 4 facts being provided, now we get closer to the statement and the proof of the Arzela Ascoli theorem itself. So gear yourselves up for some really interesting stuff. Okay, so now we start with the proof. First, the statement of Arzela Ascoli and then with its proof. So the statement goes as follows. If f is a proper subset of the continuous functions on the real interval 0, 1, closed and bounded, which is closed, and f itself is closed and bounded, then it follows that f is compact if and only if f is uniformly equicontinuous. We obviously need these 2 conditions of f being closed and bounded, as you will see in the proof. So we start with first the forward direction. We'll first suppose that f is compact and we will show that it's uniformly equicontinuous. As is generally the case with many of these if and only if proofs, one direction turns out to be very trivial and the opposite direction turns out to be highly non-trivial. So the forward direction is one such example. It's very trivial. If f is a proper subset of the continuous functions on 0, 1, such that f is compact, then we know from the previous theorem that we showed on the previous slide that f must be totally bounded because any compact set, any compact subspace of any metric space is completely and totally bounded. So it must be totally bounded, and since it is a family of functions that is in C01, it being totally bounded implies that it is uniformly equicontinuous, and that it's as simple as that. That's the forward direction. Now we we commence with the reverse direction, which is highly non-trivial but is very gratifying and very satisfying. So we suppose that a family of functions is a proper subset of C01 continuous functions on 0, 1, such that it is uniformly equicontinuous and such that it is bounded. We need these 2 conditions in order to prove our theorem. So now we may first make use of the fact that the family is uniformly equicontinuous. So there exists a positive delta, so that for all x and y in our interval 0, 1 and for all functions f in our family, we have that whenever x and y are within delta of each other, the image points f of x and f of y are within epsilon upon 2 of each other. And we are choosing epsilon upon 2 for a particular reason, as will become clear towards the end of our proof. Obviously, we've chosen an arbitrary epsilon at the start, and we want to show that our family is totally totally bounded, and hence it will be compact. So now we know that it is. We've chosen the delta in such a way. Now what we do is we define a natural number m in such a way that m is defined to be the minimum of those natural numbers k, such that k delta is greater than or equal to 1. We will see why this definition of m is necessary and how it can be implemented in the proof. Obviously, we can assume without any loss of generality that m is greater than or equal to 2. There's no harm in assuming that. With m defined in this way, we now subdivide the closed bounded interval 0, 1 into m subintervals of the form d sub j defined to be j minus 1 delta to j delta, where we're very particularly including the left bound but not including the right bound. So that's why the left bound is closed and the right bound is open. We're doing this so that we can partition it. We can partition the interval into m sub intervals, which are neither open nor closed, because one end is included, one end is not. And this j holds for j between 1 and m minus 1, and obviously we have not defined what d sub m itself is, so now we will define what d sub m is. We will put d sub m to be the closed interval m minus 1 to delta and 1. Obviously we need to now include this last endpoint 1, so that's why the definition is a little asymmetric, because we are including the endpoint 1, the right endpoint 1 in d sub m, but we are not including the right endpoint in any of the d sub j for j less than m. This is so that every element in our set is in at least one of these intervals. Otherwise, one would not be in any interval, so we need to partition the set. Now, next, we've defined our sets d sub 1 up to d sub m, which are a subdivision of 0, 1. Now, we know that f is the family of functions f is bounded. That means that its supremum norm is less than some positive real number, and the supremum norm is the supremum of the image or the magnitude of the image over all x in our interval, which is 0, 1. So that means that obviously we are choosing 0 as our the center of our ball in order to bound it, and then we're showing that we take the 0 function, and that every function f in our family has to be less than some finite number, positive finite number away from our 0 function in the supremum norm, and the supremum norm is what induces our metric here. So there exists a positive real number, so that for all functions in our family, we have that the norm of f, the magnitude of f of x is strictly less than r for all x in our interval 0, 1. Obviously, because this follows from the fact that our family is bounded. Now, we set n, earlier we defined m, now we're defining n. Now, n will actually correspond to a subdivision of the codomain. M corresponded to a subdivision of the domain. N will now correspond to a subdivision of the codomain. So we define n to be the minimum of those natural numbers k such that k epsilon upon 2 is greater than or equal to 2r. And the reason we're choosing 2r over here is because the length of our interval minus r to r, so our interval minus r to r is of length 2r, and that's why we're choosing the minimum k so that k epsilon upon 2 is greater than or equal to 2r. Because then this will help us induce a subdivision, a proper partition of the codomain, which is minus r to r, which is, in fact, the codomain is all of r, but we know that the image is properly contained in minus r to r. So with n defined in this way, now we subdivide minus r to r into n subintervals, okay, of the form I sub l, for L between 1 and n minus 1, for L between 1 and n minus 1, to be minus r plus L minus 1 epsilon per 2 to minus r plus L epsilon per 2. So each of these intervals here has length epsilon per 2, and in the case of the partitions d sub j for the domain, each of the intervals had length delta. So we're using d for domain and I for image. And again, we're following the same pattern as in the previous case. We're going to include the left bound and not include the right bound, but only for indices 1 to n minus 1. And obviously the definition is going to have to be asymmetric in order for us to include the point r in the codomain. So this is only true for L between 1 and n minus 1. And for L equal to n, we place I sub n to be minus r plus n minus 1 epsilon upon 2 to r, because obviously n epsilon upon 2 is going to be greater than or equal to 2r. So when we subtract r from that, it is going to at least be equal to r. So that's why we don't need to go all the way up to n epsilon upon 2. We can just stop at r, whatever, depending on whatever n may be. Now what we've done is we reached a point in our proof where we have created a partition into intervals of length delta for the domain, and there are m of those, and intervals of length epsilon upon 2 for a codomain, and there are n of those. Now we will see how to use that in our proof. Okay, and now we come to the last segment of the proof. Here, before I start, let me just mention that I'm using the notation natural sub m to denote the first m positive integers, and natural sub n obviously to denote the first n positive integers. Now, in the previous slide, we left off by creating a subdivision of our domain into m subintervals and our codomain into n subintervals. In the domain, the subintervals had length delta. In the codomain, they had length epsilon upon 2. And obviously, the codomain goes from minus r to r, which is actually it's a subset of the codomain. And the delta was chosen so that in the definition of equicontinuity, the distance between the image points is less than epsilon upon 2. So the reason we're choosing epsilon upon 2 is suggestive of the fact that we're going to have two copies of epsilon upon 2, which will then sum up to epsilon and then give us the proof that our family is totally bounded. So we first consider the collection blackboard bold psi of functions, little psi from n sub m to n sub n. So that's the first m positive integers to the first n positive integers. Now we just want functions. We are not placing any condition of surjectivity of it or it being one to one. Or we only require that it is well defined. So different. We know that the cardinality now of blackboard bold psi is exactly equal to n sub m, and that's really not so important. What's really important is that it is finite. It's finite. It's a finite number. There are only a finite number of such functions from the first n natural positive integers to the first n natural positive integers. Now, for each psi in blackboard bold psi, we create a new function g sub psi. We create a function g sub psi, which is a bounded function of 0, 1. It's not necessarily a continuous function. Which is a bounded function 0, 1. But it happens to be a step function, and it's defined in such a way that for all j in n sub m, we have g sub psi of x equals minus r plus psi of j minus 1 times epsilon upon 2 for all x in d sub j. And obviously d sub j takes the form j minus 1 delta to j delta, with the left endpoint being included and the right one not being included, or d sub m for j equal to n as m minus 1 delta to 1. So what's happening is that on the interval d sub j, we first compute the value of psi of j, which is defined because psi is a well-defined function from n sub m to n sub n, and then we map every x in d sub j to the left endpoint of the interval I sub psi of j, I sub psi of j. So we know that I sub psi of j takes the form minus r plus psi of j minus 1 times epsilon upon 2 to minus r plus psi of j times epsilon upon 2. In general, if it's just equal to k, then I sub k is minus r plus k minus 1 epsilon upon 2 to minus r plus k epsilon upon 2. And obviously the left point will be included, the right won't, or for the last one, the right will. And now this is a well-defined map from the set of functions, from the set of functions blackboard both side, to the set of bounded functions 0, 1. It's well-defined. Now we also define another map, capital phi, cap phi from our family of functions f to blackboard both side by f in our family gets mapped to cap phi of f, where for each j in n sub m we have now the cap phi in f is a member of blackboard both side. So obviously it's a function from n sub m to n sub n. So we need to define what cap phi of f does to each element in n sub m. So for each j in n sub m, we have phi of f applied to j equals k, where we take the left endpoint of the subinterval d sub j, which is j minus 1 delta to j delta. The left endpoint is j minus 1 delta, and we evaluate f at it. And then that, by definition, should lie because all the images lie within minus r to r. That should lie in some subinterval I sub k, where k is between 1 and n. So that is that's the exact mapping that we defined. So cap phi of f sends j to k, where f of j minus 1 delta lies in I sub k, and this is well defined because f is a well defined function, and also because the codomain is well partitioned into these n subintervals, and so is the domain well partitioned into these m subintervals. In fact, it's more important that the codomain is subpartitioned here for this particular function cap phi to be well defined. So we have cap phi is well defined. Now we claim that the finite collection G sub psi, where psi runs in elements runs through the elements of blackboard bold psi, or blackboard bold psi, provides the net that bounds the family F. So now, indeed, we have that for every x in D sub j, for j between 1 and n, we're going to show that we're going to show that the distance between f and the supremum num and g sub cap phi of f. G sub cap phi of f is now a well-defined step function, because cap phi of f is a well-defined function from n sub m to n sub n. So that means that g sub phi of f is a well-defined step function, which is also bounded from 0, 1 to r. So we're going to show that this distance is less than or equal to epsilon, and that will complete the proof that all our functions f in our family are within a distance epsilon of this important finite number of bounded functions in 0, 1. So we have for x in d sub j, f of x minus g sub cap phi of f applied to x using the triangular inequality is broken up into two parts. This part, the left component and the right component. So the left component is the norm is the magnitude of f of x minus f of j minus 1 delta, which is the left point of d sub j, and x also comes from d sub j. And then again we have to subtract this quantity, f of plus the magnitude of f of j minus 1 delta minus g of cap phi of f applied to x. This is a simple triangular inequality, which is the fourth axiom that any metric space, any distance functions should satisfy. We know that because x lies in d sub j and j minus 1 delta also lies in d sub j, we know that these 2 points on the argument, x and j minus 1 delta, are within delta of each other, and so their image points have to be within epsilon upon 2 of each other. That's the first part taken care of. Now the second point, we know that g sub cap phi of f applied to x is a step function, and it sends every point in d sub j, in this interval d sub j, to the left endpoint, to the left endpoint of the interval in the codomain I sub k, where k is given by phi of f of j. So we have so we know that g sub cap phi of f applied to x will give us minus r plus cap phi of f applied to j minus 1 times epsilon upon 2. And we also know that f of j minus 1 delta was one of the elements that also lied in the same interval of the codomain I sub k. So f of j minus 1 delta lies in the codomain in the subinterval I sub k, and so does g sub cap phi of f of x, because they're both in the same subinterval of the domain, because j minus 1 delta and x both lie in d sub j. So because they're in the same interval d sub j, they must also get mapped to the same to the same interval in the codomain, which is minus r plus cap phi of f applied to j minus 1 epsilon upon 2. Now, we know that f of j minus 1 upon delta may not be equal to the left endpoint of the interval I sub cap phi of f j, which is I sub k. It may not be equal to the left endpoint. We only know that f of j minus 1 delta lies inside I sub k. We don't know that it is equal to the left endpoint of I sub k, and hence this distance between these two terms may not be 0, but it is certainly less than epsilon upon 2. And hence these two values sum up to epsilon, and that gives us the final answer. So then if we take the supremum over all j between 1 and n, and over all x in each of the j's, then what we get is that the norm between f and g sub kappa phi of f is less than or equal to epsilon. And now obviously there's one caveat that we need to look at. We've shown that for any function f in a family, we can find a bounded function such that that function forms the center of a ball of radius epsilon in which f is contained. But there's this theorem in total boundedness which says that now if we can find a net such that it covers our space with open balls with centers outside of our space. So although these centers, the G sub kappa phi of f, are not functions in our family f, and nor are they continuous, because we can bound them from f by this quantity epsilon. It means that there exists another net which for which the centers of our balls are members of capital F, members of our family F. So indeed, we now get this final statement that F is contained in the union over F in our family of the balls whose centers are G sub kappa phi of F and with radius 2 epsilon. Obviously, we have to take a radius of 2 epsilon now because we've only shown that it's less than or equal to epsilon, and we need a strict inequality. And obviously, this is a net that covers all of F with open balls. And the centers are not members of our family F, and nor are they continuous. But because we can find such a net, we can also find a net where this consisting of balls whose centers do lie in our family. And that's the proof. And I hope you have enjoyed this.